Okay, so this is the third topic. This is C under things you need to know for the AP exam. This we're about to cover electric circuits, and I'm going to talk about all of these things about electric circuits in this video, which should be maybe 10 minutes. So the first part would be current, resistance, and power. Current is the rate of flow of charge. So it's dq dt. It's how fast the charge is flowing. It's measured in amps. Yeah, that's about all there is to that one. I'm not going to go through drift velocity right now. That would be a minor topic on the AP exam. Resistance. Resistance is opposition to the flow of charge. It is defined, if you're using Ohm's law and a material that obeys Ohm's law, then we've got V equal to IR, so it's the change of voltage divided by current. If you're not using, for anything, the resistance is rho times the length of the resistor divided by the area of the resistor, cross-sectional area. And these are the values for the resistivity, that rho value. Also, the resistance for something will change with temperature. Generally, as the temperature goes up, the resistance goes down. But that's a very minor part there. Power. Power is the rate at which work is done. Oh wait, here's resistance and temperature. So there's a lovely formula. You just plug it in. Oh, I'm sorry. Resistivity tends to go up as temperature goes up, so you get more resistance. Excuse me. So if resistivity goes up as temperature goes up, then when does an incandescent light bulb carry more current? It would carry more current when there is less resistance, and there would be less resistance when the temperature is lower, which would be right after you turn it on. All right, power. I'm not getting into superconductors right now. Power is the rate at which work is done or the rate at which energy is used. If you combine all the types of power here, and you say power is, where's the one I'm looking for? Here we go. QV, which is, we know that QV is work, or the negative change of potential energy, correct? Divided by time. Well, this dq dt term is current, so power for electrical circuits is current times voltage. But it is still the rate at which work is done. And that's just substitution with Ohm's law. All right, so these are the concepts. Here's current. It's measured in amps. Resistance. It's measured in ohms there. I'm not getting to that one. Not getting to that one. Resistance there, resistivity. Here's the temperature. And then power. Next chapter, which is still talking. So DC circuits. So the electromotive force of a battery is the maximum possible voltage the battery can provide between its terminals. In other words, it is the potential difference when there is no current running. If you're going to talk a battery and it says that it has this much internal resistance, you would put that battery with its EMF in series with a resistor there. And then that would come out and be the rest of the circuit. if you were going to look at this, the voltage of this battery would be this IR value, because that's the difference between this terminal of the battery, the cathode, and this terminal of the battery at the anode. Sometimes it's called internal resistance, sometimes it's called load resistance. Just understand that if you're talking about an ideal battery, it has no internal resistance. If it does, you just put the battery itself with its EMF in series with a resistor. All right, resistors. If resistors are placed in series, you add them to develop their equivalent resistance. And the current would have to run through each one of them in turn, because there are not multiple paths. There's only one path for the current to take. If resistors are connected in parallel, like this, there are multiple paths for the current to take. The difference in voltage across both paths would be the same, but the current may be different through each path. And as a result, the equivalent resistance is this 1 over Req is equal to 1 over R1 plus 1 over R2. Back to series circuits. For a series circuit, you will have the same current through the entire circuit and a different drop in voltage from A to B than necessarily from B to C, depending on the values of the resistors. Because for voltmeters, you always want to measure the voltage across a circuit. You always connect voltmeters in parallel with the component you're trying to measure. And because for ammeters, you are always trying to measure the current through a particular component, you always connect ammeters in series with that component. Kirchhoff's rules. There are two of them, loop rule and the junction rule. The loop rule says that all of the current going into a junction has to equal the current coming out of a junction. So for example, I1 would equal I2 plus I3, because I1 goes into A and I2 comes out and I3 comes out. So I1 is equal to I2 plus I3. That's called the junction rule. The loop rule says that the sum of the potential differences across all elements around any closed loop must equal 0. So that means if I start at A, I3 times 9, which is the value of that resistance, will equal 18 volts. Or actually, let's start at B. I'd prefer there. If I start at B, then A has a value of, if B has 0 volts, then that's 18 volts, and the current through path 3 is 2 amps. And we've done some problems with those. And that's it for basic circuit rules. Then we're going to add capacitors to the circuit. If you add capacitors to a circuit in series with resistors, it's called an RC circuit. What I really want you to understand is that capacitors, if they're operating in steady state, a capacitor, the charge will build up on a capacitor. If I were to close the switch between A and this point, then the current's going to run out of the battery here. It's going to run straight through this capacitor, and it's going to run through the resistor and back this direction. But the current actually is the rate of flow of charge. What's going to happen is charge is going to collect on this resistor, and then an equal amount of charge will come off of this this conductor, and then an equal amount of charge will come off this conductor and run this way. And charge will build up on the capacitor until charge stops flowing. As you charge a capacitor, as you close this switch, charge will build on that capacitor until charge stops flowing. Capacitor begins to charge up. When the switch is thrown to position B, it will discharge, and we're going to talk about both of those situations. If the charge is building up, it is not at a linear rate. Instead, this is what you need to know. The charge that is present on the capacitor is equal to Q max times 1 minus e to the negative t over RC. This RC term is called the time constant. It's also represented with a tau. And basically what that means is you start off with no charge, and the charge builds up to a maximum asymptotic value of Q sub R. So there it is. No charge, and it builds up to this maximum value of charge, which is C times the voltage, or C times the electromotive force. Again, tau is the point at which it's built up to 0.632%. I'm sorry, yeah, 0.632%, 63.2%. Y'all see what I'm doing there. 63.2% of that. All right, the current, as a result, will flow pretty quickly at first, but then it will slow down and slow down and slow down because once this capacitor is fully charged, there will be no current running through it. So the current will go to, this is the maximum current, the electromotive force divided by R, that's based on Ohm's law, times e to the negative t over RC. The current will slowly start at maximum and decrease. So after one time constant, it will be at 36.8%. Notice these add to 1. All right, when you are discharging a capacitor, the current will slowly come off of it, and it will look just like what we just saw for the current for the last one. You'll start at maximum charge, and it will slowly decrease like that. Again, the graph will look identical to what we just saw for charging. When we were charging a capacitor, the current graph looks identical to the discharging a capacitor charge graph. And again, the current will slow to 0. Okay, the current will run off the capacitor at first, but then it will also slow to 0. So this graph, I wish they had it in your book, but I've got it. As you discharge a capacitor, the current does this, and the reason it's negative is because it's moving in the opposite direction. So that's why it's negative, but it's still reducing just like the charging graph. Charging and discharging graph are mirror images. Actually, let's see if I can do that. There's charging, discharge voltage. Voltage goes down because the current's reducing. And the current is also reducing. And I think that is it for that third section there. We've gone through. And we'll do magnetic fields and electromagnetism soon, and then I'll go back and get some of the math for some of these math examples. Hope that helps.